Hello class. Today we're going to be discussing more on exponents, and we're on lesson number 6, and we're in the powers of products and quotient. Now, one of the most famous formulas of this century is the result of Albert Einstein's discovery that the amount of energy contained in an object is related to its mass, and the formula is E is equal to mc squared, in which E represents energy, m represents mass, and c represents the speed of light. Now, the speed of light is 3 times 10 to the 8th power meters per second. Squaring this number, as the formula indicates, we would have 3 times 10 to the 8th raised to the second power. So let's take a look at what they're doing here up on our board, so that we understand how to raise and or of the powers of products and quotients as the title, but we're raising powers. We're going to be handling this very carefully. Sometimes we tend to jump quickly in math and not realize that we're making a mistake, because visually we may just look at this and say, well, I'll apply the exponent over here to the 8, and that would be a mistake, because we know that what we're basically doing here is multiplying 3 times 10 to the 8th power times 3 times 10 to the 8th. That looks more like an x. Let's see. Really, the x we don't normally use in multiplication, but it is used scientifically, and you'll notice it's a very straight x, and it's not italicized. So let's make ours look a little bigger there. So now we have the expression parentheses 3 times 10 to the 8th power, and parentheses times parentheses 3 times 10 to the 8th power. Now we know that we can just go ahead and group these and multiply them out. We would have, because we can remove over here the parentheses, simply because we're just multiplying all the way across. Had this been addition, we would not be able to. We would definitely have to multiply using whichever method. Particularly we use the FOIL method, and we'll learn more about that later on when we deal with polynomials. And FOIL stands for first, outer, inner, and last. But anyway, let's go ahead and multiply 3 times 3. We can group these. And then we have times. They actually put the times there, but we can just keep this all in parentheses, because we know that the parentheses does represent multiplication. So we have 3 times 3 times 10 to the 8th times 10 to the 8th. Now we can go ahead and multiply 3 times 3, and we get 9. And I guess they put the x in there because they wanted to put that x, or that multiplication sign. Let me not call it the x, but the multiplication sign. And we now can, simply by multiplying, what do? We add the exponents, and we get 16. So when we square 3 times 10 to the 8th power, our result is 9 times 10 to the 16th power. So if we substitute it back into the original equation, and and our equation was E is equal to mc squared, we would now, and let me just sort of put a line over here, sort of denoting that this is going to be something different. Now we have E is equal to 9 times 10 to the 16th power times mass, m. Now take a look at what that is. Or E is equal to 9 with a bunch of zeros, right? Well, there's 16 decimal places there. In fact, there'll be 16 zeros if we sort of roll it back. I go to the right side and roll it back. I have thousands, I have millions, I have billions, I have trillions. So that will be 90 quadrillion times m. Now let's turn over to page 372. Apparently, the amount of energy contained in even a small amount of matter is tremendous. Matter contains a lot of energy. It can be shown from this result we have obtained that in fact that the amount of energy equivalent to the mass of a single glass of water would be sufficient to run the entire United States for several hours. In finding the square of the speed of light, we found a power of a product. The result suggests another way to find it. Now let's take a look over here. They took a different approach, and they expressed, I tell you what, let's go ahead and just remove this. Oh, not what we were trying to do. And let's get rid of our menu up here. But let's just go ahead and look at how they're expressing it. And we'll keep it up to here. And when we took, they actually had placed them both side by side, but we know that we can simply apply the exponent, simply say 3 squared times 10 to the 8th power and square that. Is that not really what we did here? Well, we ended up with what? 9 times 10 to the 16th power. Okay, because we're entering what's called the fourth law of exponents. And what the fourth law of exponents is, we have x times y raised to the a power. Okay, so this is our fourth law. And x times y raised to the a power is going to be equal to x to the a power times y to the a power, which means we actually will apply the exponent to both or all factors that are found within the parentheses. Now again, we must be very, very careful here, and we'll learn more about this as we enter into polynomials. This is not the same as, and I'll tell you right now, x plus y squared. This is totally different. And we could just take a look at and put some simple numbers in here so we can see. I like to prove it with the simple numbers. Let's say we had x is equal to 2 and y is equal to 3. Okay? So if we were squaring this, and if we tried to do the same, is this exactly the same? Are we allowed to do, oops, sorry, we're going to put the values in. And I'd like to show you why it's the wrong way. Okay. First off, we can see that 2 times 3 being squared is not the same. Oh, I'm sorry, I put 5 there. 2 plus 3, which is 5. I was thinking ahead. These values are not the same. And therefore, we have to be careful that we try not to do this. X squared plus y squared. You might say, and I'm raising is squared, or let's say this were a. It's trying to follow the same pattern here, but let's say we're squaring. Well, let's say we have 5 squared, and that would be 25, right? Now over here we would have 6 squared, and that would be 36, okay? Now, what if we tried to apply this method over here? Well, we would have had, and let's just go upward, we would have had 2 squared times 3 squared, which is equal to 4 times 9, which is equal to 36. So we see that we can go ahead and apply this. It works either way here. But if we try to do the same thing here, and we will naturally try to apply this exponent, and again this should have been an a. If we try to do this, which this is wrong, I'll tell you why. Well, what happens when you get 2 squared? You would have 2 squared would be 4, or let's go ahead and write it out. Well, 2 squared. And again, if we took the wrong method, and plus 3 squared, well, what do you have? Well, you end up with 4 plus 9, which is 13. Now, as you can see, 13 is not equal to 25, and we know that the answer here really is 25, because all we have to do is add what's in the parentheses and raise it to the power, which we did, which would have been 25. So we can see that this is not the approach. And I like to bring that out to the class, let them know ahead of time that you must be very careful. You're dealing with multiplication here with these exponents. And whenever we have any expression, really factors, such we have here because we're talking about multiplication, x, y, we can raise this to the power and simply, and I'll use this term loosely, distribute the exponent to each of the factors that are inside. The term factors is used because we're multiplying here. These are actually terms because we're adding them. So remember, we must be dealing with factors at all times. We also can now derive our fifth law. Let's pause for a second. Okay, we'll continue. Yeah, it just disappeared, didn't it? Yeah, modern technology allows me to pause, clean it up, and we could now have more room for the fifth law. And the fifth law, because remember, multiplication and division, how closely related they are. I call them cousins. If it holds true for multiplication, then it should also hold true for division or the power of a quotient. So let's take a look here. In the fifth law, if a is an integer and y is not 0, we then can say that, put the fifth law here. Oh, I need to get my pencil back. Our fifth law, not easy using these pen tablets, I'll tell you, but I'm getting better over time. We have x over y raised to the a power, and that's going to be equal to x to the a over y to the a. So we are applying here again the exponent, and you know, we can always express, I'll bring it over here, x over y is equal to x times 1 over y, right? And if we were again squaring or applying, let's use the a, we're raising it to the a power, and if we're doing it here, then we know that we could go ahead and apply it. We'd have to apply it to both of these. And if we applied it to both of these, we would end up with, let's go back down here, as we did up here where we applied, or the fourth law, x times y raised to the a power, we would distribute, and again I use that term very loosely, the a, or the exponent, and we would have x to the a times 1 over y, right, to the a power. Now you might say, well, how can I express this? Well, that would be x to the a times, I guess we should probably use an example here. If we're using the number 2, maybe I should use this as an example so we can better illustrate. Let's substitute the number 2 for a. We would end up with x squared times y, 1 over y, times 1 over y. Would we not? And when we multiply, we know that when we multiply, we should be multiplying the numerators and the denominators, which means we would have x squared times 1 times 1, which is 1, over y times y, which is y squared. So we can see that when we applied this exponent to 1 over y, and as we did in this case, we see that the exponent applies to the lower, to the denominator, because 1 times 1 will always be 1. And essentially, we've come all the way back to x squared over y squared, right? Which again just goes to prove that x over y raised to the a power, x over y squared, would be x to the a divided by y to the a. It means that the exponent is applied to both the numerator and the denominator, and we kind of went through this the long way to sort of prove that. And we use the example of 1. We could have used any number. We could have used 3 and simply put 1 over y times 1 over y times 1 over y, and we would end up with 1 over y cubed. So you can see how, just sort of rolling it back, why this is so. Now, these properties of exponents, like those studied earlier, work even if the exponent is 0 or negative. And we have some examples over here. We have example number 1. Let's clear up the board again. And now that we have our board cleared, we can take a look at example number 1. Write an expression without parentheses equivalent to negative 4x squared. So we'd have negative 4x squared. And this is going to be raised to the third power. Okay, so according to the fourth law, we can go ahead and raise each of these factors by the power. So we would end up with negative 4 cubed, or to the third power, times x squared to the third power. And then that would be equal to negative 4 times negative 4 would be 16, positive 16, but then we would multiply by negative 4, which would make it negative 64. So we'd have negative 64, and if we raise x squared to the third power, we know that by applying, I believe it's the third law, we would then have x to the sixth power, and yes, that is the third law. We would have x to the 2 times 3, and the 2 times 3 would be 6. So we'd have negative 64 times x to the 6th power. So now we wrote the expression without parentheses. That's equivalent. So that was the instruction we were given. Let's take a look at the next one. We have find 3 times 10 to the negative 5th power in parentheses. All right. So we'd say 3 times 10 to the negative 5th power, okay, in parentheses, and that's going to be raised to the 4th power, okay? And we are to express the answer in scientific notation. Very important that we follow the instructions. Sometimes you'll get answers, I'll get answers from students, and they'll do the multiplication all the way through and they'll express it maybe in decimal form. Well, you really may have answered it along the way, but your final answer was incorrect because it was not given according to the instructions. So we're to express the answer in scientific notation, and we understand what that is. So let's go ahead and do that. We would raise 3 to the 4th power. Right, so it's 3 to the 4th power, and that's time. So we're going to preserve that x there, that big multiplication sign, and we're going to have 10 to the negative 5th power, and we'll raise that to the 4th power. So what do we get? Well, 3 times 3 is 9, times 3 is 27, and times 3 again would yield 81. So we have 81 times negative 5 times 4 is negative 20, so we have times 10 to the negative 21st power. Now we may think, excuse me, to the 20th power. Okay. Now we may think at this point, well, we're done. Well, it's not truly in scientific notation. Why? Because 81 is being expressed. It's the expression to the left here, and we know that scientific notation that this number has to be one or greater than or equal to 1, but less than 10. And this is greater than, or this is definitely above 10. So we know that we need to move a decimal point over, and we can express, I kind of like the way they expressed it over here, 8.1. Okay, but what's that? Well, that's 8.1 times 10 is equal to 81, would it not be? So we know that 10 is 10 to the 1st power, and now we just simply tag along our 10 to the negative 20th power. Now we can see where we're going with this. We're going to have 8.1 times, and we can go ahead and multiply these two. They have the same base, So we can add, and when we add positive 1 and negative 20, we get 10 to the negative 19th power. Okay, so this is now in scientific notation. Now, just pause for a minute, and something that I try to show my students, that we saw that this number, 81, went down to 8.1. Right? And when this side of the multiplication sign goes down, then you need to raise a power here, because we need to create an equivalent expression. Now, it seems a little bit strange because we actually have a negative 20. And raising the power of negative 20 would actually reduce the number to 19, because remember, it's negative 19, it's coming closer to the 0, so it's actually getting bigger. So it's a little bit tricky. You have to be careful. I like the way they expressed it here by simply expressing the 81 as 8.1 times 10 to the first power, and then simply multiplying it by 10 to the negative 20th power. Now we can see same base, just simply add the numbers, and when you have positive 1 and negative 20, that will yield negative 19. So as we can see, as this number went down, this number went up, though again, dealing with negatives, it looks a little bit tricky. Okay, now let's just take a look at the last problem. They have 10 to the negative 2 to the negative 10 power, up here in this top corner, and that is being divided by 12 to the negative 10 power. Now this is a bit tricky because we want this as a power of 6. So this is going to take quite a bit of work here to undo and redo, let's say, the expression. We're going to really have to work hard here. Now the first thing we ought to do is, knowing the fifth law of exponents, is that we can express this as a fraction. Okay, now when we say as a power of 6, we need it as 6 to the something power. Okay, somewhere along the way, down here at the very bottom, a power of 6, it means 6 to the something power, let's just say. That's our goal. That's what they mean by power of 6. So now, for us to do this, we have to unwind this, and we can, because we see, knowing the fifth law, that we can extract this exponent, put it on the outside, as they did. So we have 2 over 12 to the negative 10th power. Okay, so it's just the opposite of what we were doing when we're applying it. We're going backwards, and this is something that's very important with algebra, and you're going to be doing a lot of factoring in the future. So it's good to be able to see both ways. It's sort of like you take a trip somewhere and you drive there and you sort of make note of the different landmarks, and it helps because when you come back, you could see those same landmarks and say, yeah, I know I'm on the path coming backward. So or coming back to your original your original destination. Or from your original destination, let's say. So if you're looking at this, you would have to extract the exponent, because we need to have something, or the number 6 to some power. So now we actually have 12 divided by, or 2 divided by 12, which we can now simplify and say 1/6, right? Now this is where it gets interesting. To the negative 10 power. So we're just bringing it over here. So we have 1/6 to the negative 10th power. Now, what happens when we apply a negative power? Well, let's go ahead and do this. We can say that, excuse me, 6 to the negative first power raised to the negative 10th, 1/6 is basically 6 to the first power. And if we wanted to express it this way, we can certainly do so by saying 6 to the 0 power. Okay. And 6 to the 0 power is 1, by the way. And 6 to the first power, we know that we would subtract 1 from 0, and we'd have negative 1. So we can express this 1/6 as 6 to the negative first power. So now we have an opportunity here Let's just go ahead and remove this part here. So we have now converted the 1/6 to 6 to the negative first power. And now we're at the 6th power. Now we simply just need to multiply the negative 10 times the negative 1. Okay, we're back to the 4th law, and we're going to get 6 to the 10th power. So as you can see, when you look at 2 to the negative 10th power and 12 to the negative 10th power, and for us to express this as a power of 6, we would go through a little bit of a process here of separating our number turned into a 1/6, which we can express as a 6 to a negative exponent, which now allows us to simply multiply. So it's a little bit tough, a little tricky, but again, we have gone in one direction and now we went backwards. So this one's a very challenging problem. It forces you to think a little bit outside the box, so to say. But we know we could have actually done something else, and I'm going to bring that all the way over here. I'm going to shoot over to the other side. And we know that we could have expressed 2 to the negative 10 power divided by 12 to the negative 10 power. We can change these to change the negatives to positive by simply expressing like this: 12 to the 10th power, excuse me, that's a 10, and divided by 2 to the 10th power. Okay, and why can we do that? Well, we understand when we go back to the, I believe it's the third or the, let's turn back, you can turn to page 361. We know that we can apply the second law, and in doing so, the second law really reveals a lot more than the law shows itself. But I can subtract, I cannot subtract these two because they are not the same base. But by moving one to the top and the other one to the bottom, I'm actually turning them from positive to negative, and we'll go over that in some of the exercises later. But that's basically what you are doing, as we did over here. 1 to the 6, or 1 divided by 6 to the first power basically puts 6 to the negative first power. So we can do the same thing here. We kind of swap them. And what do we have? Well, we can just take 12 divided by 2 and raise that to the 10th power. And what do we have? What's 12 divided by 2? Well, that's equal to 6, and that's raised to the 10th power, which again is the same answer that we had over here. So, okay, so that's the end of this class.